Yes. So as Ruth said, I'm a postdoc at Bernard's lab for the last 3 years, and before that I did PhD in Russia. Some of you already visited our practical on learning theory. So you may ask, why is the learning theory talking about this very applied and hyping field? Which is a reasonable question. And the thing is, for the last half a year, I would say, we started looking into the generative adversarial networks, mostly from a theoretical perspective. And of course, then we ended up running all these deep nets on clusters, and we gained some, applied knowledge. So now a couple of announcements. First, you will not learn about all the tricks and hacks to train GANs in this talk. I am not an expert for that. So rather, the goal would be to pass you some knowledge, essential and, sufficient for you to enter this field of generative unsupervised models. As you know, there are many, many hundreds of papers being published, submitted. Everybody working on it right now. Every single day there are new papers called something GAN, which are improving and improving the already existing models. So back when I started, learning about this field, it was a nightmare to read all these papers. So our goal, my goal, is kind of to pass you the knowledge in a short format within next, actually 1.5 hours, so that you will have a big picture of what is happening, and you will be perhaps then able to actually attack this field on your own. Yeah. So, and this is the contents at a glance. So shortly, I will start with introducing the problem of unsupervised generative modeling, and I will try to fix, to explain a particular type of models we will be focusing on. Then we will shortly discuss how do you actually compare probability distribution, because this is something you should be doing if you are doing generative modeling. Then we will actually dive into the real algorithms, and I will start with a class of algorithms which are nowadays commonly known as adversarial training. I will start with original GAN, generative adversarial nets, and the more general version FGAN. These guys are minimizing the so-called F divergences, which are distances between probability distributions, and they are doing it from the dual formulation. We will see this concept of dual. Then I'll pass to the WGAN, which is by now considered to be one of a very good, algorithms for training GANs. This guy is actually minimizing the optimal transport, the Wasserstein distance, and again from the dual formulation. And these things will be important in my talk. Basically, I will try to emphasize the fact that in the field of the generative models, there are two types of approaches. One approach the problems from the dual formulation, and another from the primal. And we will discuss it later, but yeah. So WGAN is minimizing Wasserstein distance from dual. After this, we will look at more classical variational autoencoders, which are minimizing the KL divergence or the marginal, or maximizing the marginal log likelihood, and they are doing it from primal formulation. So KL divergence is an element of F divergence. So in principle, you could say that GANs can be minimizing KL divergence, but they would do it from dual formulation, and we will here discuss the primal formulation. And finally, I hope to have a time to talk about this recent development, which is called penalized optimal transportation. We will talk about minimizing the optimal transport from the primal, not from the dual, from the primal. And then I will summarize the difference between these dual versus primal approaches, and and discuss some further open questions. And mainly, I want to stress this. So on every slide, this big flashy statement will appear. So there is indeed there are no adequate ways right now to evaluate this model, which is a big, big problem of this, in my point of view. So mostly people compare models either, visually, saying, my samples look much better than your samples. And this is something which can be done in the early stages when, you have some model which is doing really bad, and then you come up with a model which starts performing significantly better. And, then the visual difference may play a role, and you can base your decisions on a visual comparison. But right now the field is already at this stage when improvements are becoming not so obvious. And you need a very, unified and adequate way to evaluate the models. And this is something missing in this field. And yeah, I think people should concentrate on developing these evaluation measures. This would perhaps lead to further improvement. Okay, and we will start with introducing the problem, actually. So, okay, what are we trying to solve? Imagine you have some unknown true data distribution Px over some data space X. So this could be like space of your 28 by 28 images or whatever else you want. And then we have an IID sample from this distribution, which is your training sample, unlabeled training sample. So you have a bunch of pictures. I don't CFAR 10, let's say. Now your goal is to find some model distribution PG, which you can tune, which will be similar to the unknown true data distribution Px. Okay, now the question is, what does it mean to be similar, actually? This is a big question, and I will be discussing this in next few slides. Okay, what type of models will we work with? And we will work with the so-called latent variable models, so which are described in two-step procedure. So first, you sample the so-called latent code Z from some latent space G calligraphic. You can think of this space as, let's say, Euclidean space of, some low dimensionality, let's say 20 to 100. Just, 100-dimensional vector. And actually, I didn't say usually, you define some prior distribution Pz over the latent space Z. Let's say Gaussian, standard Gaussian on 100-dimensional Euclidean space. And then you map this code Z using certain transformation G, which maps from the latent space to the true data space, which can be also random. And you obtain your image, G of Z, and you treat this as a sample from your model. So when all the densities are properly defined, you can also write down the density of the resulting latent variable model in this way. So you are integrating, marginalizing over the latent space, and this Pz is the density of your prior distribution, which I told you about, over the Z space, the one where you sample from the Z. And this is your, this transformation which I described here, which takes your latent code and maps it to the image space. But this mapping can be deterministic, if you want. It can also be probabilistic, meaning instead of obtaining a very, a deterministic one-to-one correspondence between the latent codes and the true images, you can map the latent code to a distribution of true images and then sample from this distribution, which is a more general. Okay, so all the methods and techniques which I will mention in my talk, they are quite different, but they share several similarities. And importantly, first thing, this PG model, it is very easy to sample from. Okay, given that you are not using too crazy mapping mechanism G, these models are indeed easy to sample from. How do you do that? Well, as I said, you first sample 100-dimensional vector from, let's say, a Gaussian, which is something easy to do, and then you map this vector to your image space with a certain, pre-trained mapping, which can be a deep net or whatever other flexible function of your choice. So they are easy to sample from, and this actually allows for the second point, which is all these methods which I will describe, they start from certain objective which they are trying to minimize, and it happens that this objective can be written as an expected value over Px and Pg. Okay, and this fact, it means that you can run SGD, stochastic gradient descent, by approximating those expected values based on the samples from these two models. You have an IID sample from Px, right? And I said you can sample easily from Pg. So you can do the SGD training. And this is basically how all this algorithm proceeds. Okay, now that we know what we want to do, let's discuss this notion of similarity. So you want this Pg to be close to Px. What does it mean to be close? These are two probability distributions. These are not 2 points in some Euclidean space. And what do we do? Okay, so on this slide, I show you 3 distance measures which will play important role in my future slides. So there are many other ways to measure similarity between probability distributions. These are not the only ones. There are much more. But this, for generative modeling, for unsupervised generative modeling field, these are kind of important. First class of similarity measures is called F-divergences. I will try to go quickly through that because we will see all the examples later, but F-divergences are defined in this way. So you need to choose any convex function F with certain, with certain constraints. And then for this function F, you get a particular F-divergence of this form. So you see that you are integrating, and there are some, this ratio between densities of your probability distributions P and Q, and you are integrating over Q. So it has a rather nasty form. And of course, we don't know the densities, right? In our case, P would be, let's say, Px, data distribution. We don't know anything about it. We only have an IID sample. And Q is the density of our model. And the thing is, which I didn't mention, is that this PG, it has a very, you don't have usually analytical form of density of your model distribution. So I showed you, right? This, well, you could say that, okay, this is analytical form, but this integral most often is not tractable. And especially when you start using deep nets for parameterizing these generator mappings G. So this is the case where you don't know analytical form of your model distribution, but you can sample from it. This type of models are called implicit generative models, I think. And this is why my talk is called implicit generative models. So the thing is, we don't know these densities. Okay, we don't know how to actually evaluate this F-divergence. And then how do we even minimize it if we cannot compute value? Next class is called integral probability metrics. And they are defined in this way. Basically, you choose any function class F. It should be a bounded real-valued function, but otherwise any class of your choice. And then you can define this similarity between the two distributions P and Q by doing this weird optimization problem. So you are looking at all the functions in your in your back F, and you are trying to compare expected values of this function with respect to P and Q. Intuitively, if this class is rich enough, you will find a function which makes this quantity rather large, in the case if P and Q are different, right? If P and Q are the same, you will obviously get 0. So this is a reasonable way of computing the distance. And then there is this other class called optimal transport. So imagine you have certain, similarity function of your choice defined on your input space. Basically, let's say you have a favorite way of comparing two pictures. Then you can actually leverage this distance defined on your input domain to the level of similarity between distributions. So using this cost function, you can define this quantity, which is called optimal transport. And let me translate what is written here. So, and maybe let me draw a picture. So what you're trying to do, let's say you have two distributions. One looks like this, and this would be P. And the other, I don't know, looks like this, and this would be Q. They are defined, let's say, over the same domain. What you're trying to do here, this is a set of all the joint distributions with marginals P and Q fixed. So you're considering two random variables X and Y. You're considering all the joint distributions over X, Y, such that marginal over X coincides with P and marginal over Y coincides with Q. So this is called a coupling. And then you're trying to find this coupling which minimizes the expected cost you pay to move the mass from X to Y. So basically what you are trying to do, you're trying to, so that's a real line, let's say. You're trying to find this coupling, gamma, between the points. Let's say in this case, perhaps you will map this point to this point, this point to this point, like you will say, okay, I couple these points, I couple this point. And basically, your goal is to find such a coupling that on average, okay, I did them on two different lines. I should have plotted them on top of the same real line. But you want to minimize, so let's say this is a Euclidean distance between points, okay? Let's say C is just a Euclidean distance. Then you want to find a coupling which minimizes the distance of the, of this transportation. Okay. Maybe I sound a bit weird. We will have a slide where we see better what it means. One important thing is if these two probability distributions are the same, PP, right? You can take a very particular joint distribution which just says x, y equals y. Okay? That's kind of a degenerate probability distribution. It is a joint distribution on x, y. And as I said, if P equals Q, you can take the marginals to be equal to P, and then the joint will be defined just by saying, you take a diagonal coupling. In this case, here you will get 0. So again, this is kind of a reasonable way to measure distance between probabilities. Okay, so now that we have these many different ways to measure similarities between probability distributions, let's actually turn to the algorithms, and I start with GANs. So let's say our goal is to minimize F divergence between our model and the true data distribution. So for now, let's take this as our goal, and let's try to tackle this goal. And a couple of words why this may be a reasonable goal, and why this goal actually depends on the choice of this F function. Let's consider two different cases. So I didn't tell you what type of distances are actually contained in the F divergence family. So one of them is the KL divergence. Let's say you want to minimize the KL divergence with respect to your model. Okay? So this would be one particular instance of this goal. So the KL divergence is defined in this way. Then logarithm of ratio so these are all densities, okay? So Px is density of true data distribution, Pg is density of the model. So now you see that you can split the logarithm, and there will be actually the term independent of Pg, which will be the the negative entropy of Px. So this term would be this part. It does not depend on Pg. It has no effect on our problem. So, but we have the second term, which is Px of x log Pg of x dx. Okay? So we see that if we try to do this, we will be actually maximizing this quantity, right, with respect to Pg. This quantity is a marginal log likelihood of your model. There is also this nice link to the log likelihood. Yes, to log likelihood. You can approximate this quantity because it's expected value with respect to your data distribution of certain quantity, right? You can approximate it with a sample, and you could write, in this way. And then you see, of course, you're maximizing this with respect to Pg. You see that this means doing basically maximum likelihood. So it has this nice interpretation. Another thing could be, let's just switch the arguments. So KL divergence is not symmetric. Actually, KL divergence is not symmetric. It doesn't satisfy triangle inequality. So kind of it's not a proper distance function. It doesn't satisfy certain axiom. Okay, but it is still a way to measure similarity. But if you flip it, you get you get another example of this type of situation. So this would correspond to another choice of f function. What are you doing then? Actually, you will be doing something quite different, which will be, now both terms will depend on PG. You cannot ignore them. So you will have minus entropy of PG, right? Minus this weirdly looking log Px of x Pg of x dx, okay? Or which is the same as, maximum stuff, fine. Taking supreme plus. So now, if you ignore for a moment this term, and you try to maximize this term, okay? What would your model do? Actually, it will try to put a point mass, it will try to put all its mass at the point x, where the true density is maximized, right? This is a way to maximize this term. In other words, it will find the mode of your true data distribution and put all the mass there. Now the thing is, there is this second term which says your entropy should be high. Putting all the mass to one point is kind of the worst case for entropy. So, in other words, this means, search for the mode and put certain amount of mass around this mode so that your entropy will be also quite large. And if we look at the difference between two for the case of this typical example, which you will see, imagine you have mixture of two Gaussians. This is your true data distribution, and you're trying to fit it with a single Gaussian, let's say. This case, second case, corresponds to, okay, let's say they are weighted with different coefficients. This case would correspond to finding this point and kind of, I have another color, and putting mass kind of, somewhere around here. While this case, here you want to cover all the modes. You don't want to be missing any modes because it will cost infinity to you. So you will end up doing something like this. So this, you see the difference. It matters which F you choose. This was the main message of this short detour. Okay. But both can be reasonable things to do. Oh, let's go further. Oops. Okay. So how does GAN approach this? And basically, one thing I also didn't say is that I am not showing all the references to literature. I will gather all the references in the last slide, and I will make sure that when these slides will be available online, you will have all the papers. You can look at them. Right now you see no reference. So there is this F-GAN approach, and GAN, as I said, is a particular case of F-GAN, and it proceeds using this very nice statement called Variational Representation of F divergences. So it happens that if you take any F divergence, so before I showed you, right, what F divergence is, this integral of F of ratio, there is a way to rewrite this integral in equivalent way using certain optimization problem. Okay, so this part please ignore. I mean, it's all correct, but you should not be right now depressed looking at this. So the thing is, you're taking supremum over certain real valued function t between difference of two expected values, first with respect to the first probability distribution, second with respect to the second. So now here you have t of x. This, like, right now it looks quite similar to what I showed you about implicit IPMs, integral probability matrix, right? We also had difference between expected values. But here you have this f star function on top of t of y, and f star is this convex conjugate of your function f defined in this way. So some of you already know what this is. Maybe a couple of words about this. And basically, this statement is very easy to prove. So I want to actually show you how to do that. So that you know that it's not a magic, not a miracle. It's a rather understandable thing. So first of all, any convex function f, and I told you in f divergences, f should be convex. Any convex function f can be equivalently expressed through certain set of linear functions. Basically, if you have a convex function, for every given point, you can draw a tangent line, right? Right? And then you can equivalently express this curve by taking maximum over all the linear functions smaller than this curve at any given point. This is kind of a rough idea. This is what is written there for f star of x. So this part is easy. And now regarding this equation which I have there, let me just quickly show you that it's something very easy. So this is, the formal definition of f divergence. Okay, and f is convex, as I said, right? So f can be expressed in terms of its convex conjugate using this form. I will just use this form for f. I will flip f star and f. So let's just use it. What do we get? We get supremum over this u. Now u times, I should put x there, right? And my x is this ratio. E of x, q of x. Minus, I should put f star. I told you, I'm applying it for f instead of f star. F star of what? Of u, right? I've just replaced this part. Then I still have q of x dx, right? So now I take q of x inside, which will give me no tricks. Now notice, I'm integrating over the input space x, right? And for every point x, I'm solving optimization problem with respect to u, right? And for different x, I will end up with different values of u, most likely. So why don't I say that I'm actually solving an optimization problem with respect to the function u mapping x to the real values, in which case I'm just saying that, this can be actually a function of x. In this case, I can just take this supremum outside of integration, because I will be simultaneously performing optimization in every given point of x, which is the same as finding the function, right? And then I can write sup over u of x, over u, which is now a function mapping x to the real line. Okay. What is left there? Integral over input space, u of x, p of x, minus f star of, and u is now a function, q of x, and this all dx. Do you see that this is precisely what is written there, right? Because now this is expectation of this u. Okay, so now instead of u, you now put t cap to get the notation of the state. Yeah. Sorry. Okay, I just used re-expressed convex function f in terms of its convex conjugate. I use this trick by saying that we are actually optimizing u for every given x, so optimal u can depend on x, and this corresponds to solving the variational optimization problem with respect to the function u. So I take this sup outside of integral, and what is left is precisely difference of expected values of, now I need to put down, of t of x and f star of t of y. Okay, so you see no magic here, quite simple. what does it give us actually? So the thing is, before, this had this weird form with ratio of densities. We didn't know how to compute it. Now, this value can be actually approximated by solving an optimization problem. Okay? What I mean by that, so okay, now minimizing the F divergence between this true and model with respect to model is equivalent to minimizing with respect to this G function, this expression, okay, which is the same here. Now, cool thing is, you see this expression depends on distributions only via expected values. So basically, this expected value can be approximated with a sample average over your true data points. This expected value, so okay, you see difference here, right? So y coming from your model PG is the same as first z coming from your prior distribution PZ, and y would be just g of z, as I said. This is our latent variable model. So now you replace this part with a sample average where zj's are points, IID points sampled from your prior. I told you, you can actually sample from your model distribution. And now you would be solving this problem, okay? And you can do it with SGD. And now the trick of GAN, FGAN, and all this method is you are now parameterizing your T. So this T function, this witness function in the world of GANs is called usually discriminator function and denotes it capital D. Sorry for not doing that. And this G function is usually called generator function. So now the trick is, let's parameterize T as T omega, where omega are certain parameters, G as G theta with theta parameters, and let's say these are all our deep nets, okay? Once you did this, this becomes into an optimization problem which can be tackled with SGD by doing backpropagation, which you already heard about during last week. And basically, the only thing is now you have this mini-max type of game. So you would need to start playing all these tricks of, you know, coordinate-wise SGD, meaning you first make a step with discriminator, then with generator, and continue. Okay. So this is basically GANs at one slide. Now you kind of also, okay, I have here, I just want to convince you that this is precisely, you know, the particular instance of this is precisely the original GAN. For those of you who already saw the generative adversarial nets introduced by Jan Goodfellow, so actually you can see its objective here. This is what they just put on the second page. This is a typical objective optimized by generative adversarial nets. And my point here is, if you choose very particular function f and perform what I showed you on the last slide, you will just end up with this objective. I don't want to go through this slide, like you see some. So basically, you need to choose f corresponding to the so-called Jensen-Shannon divergence. Actually, I didn't tell you also. So now that you saw KL divergence, maybe it's a time to show you what is Jensen-Shannon divergence. So Jensen-Shannon between P and Q is defined as 1/2 KL divergence between P and P plus Q over 2 plus 1/2 KL of Q, P plus Q over 2. A weird thing, right? That's called Jensen-Shannon divergence. Good thing is, okay, at least it's symmetric with respect to P and Q. You can flip them. It still does not satisfy triangle inequality. Cool thing is that square root of this satisfies triangle inequality. So square root of Jensen-Shannon is actually a metric, which is nice, kind of. Okay, apart from that, you see it also doesn't, it cannot blow up to infinity, right? So if you look at the KL divergence, where you had, okay, you remember, right? You have P of x log P of x over Q of x. If Q of x is 0 somewhere, this can explode to infinity, basically. This guy doesn't have this bad behavior because you are always comparing to the measure which is dominating your, basically you will never get division by 0 in it. So, and this Jensen-Shannon divergence is an element of F divergence family and corresponds to this particular choice of F function, which is, oh, I jump, oh, here. So this long F function. You insert it back to fgun statement, and you get the original gun. So now you can kind of say, okay, we kind of, maybe we understand what these guns are doing. It seems that they are trying to minimize F divergence between your model and the true data. Now, maybe we are actually fooling ourselves, because there is still a gap between this theory point of view and what they are actually doing. And this gap comes from the following fact. First, we replaced expectations with the sample averages. They appeared under mini-max, and you are optimizing these all things with respect to deep nets. So you heard already about uniform laws of large numbers from Shaiban-David's lecture. You can sometimes get statements saying that basically you replace expectations with sample averages, and you are still doing fine. But these type of statements are not yet available for extremely flexible deep net models, which are usually used with GANs. So there is at least gap in this respect. Now, another thing is, to get this equation, you need to actually solve the sup problem here. So you need to optimize with respect to all the discriminator functions. What we do in practice, we make this discriminator function to be an element of certain restricted family of deep nets. Of course, deep nets are very flexible. We believe that they are capable of, doing whatever we want, but it is still a restricted family, meaning that actually we are perhaps not achieving this equation. And this shows you that actually what is being minimized in GANs is a lower bound on your F divergence, right? Because instead of this sup over basically all the discriminators, we are doing sup over the restricted family, which is a lower bound on this one. So GANs, you can say, are minimizing lower bound on F divergence. And finally, okay, another thing is, apart from this restriction, in practice, no one ever optimizes discriminator to the end, meaning at every step they make maybe 2 or 3 steps of discriminator function, never taking it to the limit, which means that there is still a gap. And they do it for certain reasons, which I will mention later, for certain computational and numerical. Okay, now let me show you perhaps possible criticisms of minimizing F divergences. I mean, that's one possible one. It's not necessarily true what I'm saying here, but you could argue like that. So when your distributions are supported on a low-dimensional manifolds in a high-dimensional spaces, so what I mean by that is, what happened? I hope I will not break it. So we are talking about distributions supported on large like high-dimensional data space, right? These are distribution over the pictures, which can be 128 by 128 pictures. These are huge, huge dimensional spaces. And the point is, most likely true data distribution is supported on a low-dimensional manifold, right? Real pictures, they have certain geometric structure, and they are not just chaotically scattered all across the, million-dimensional data space. They are living on certain manifold, low-dimensional manifold. And what about our model PG? As I told you, in GANs, PG basically uses a deterministic mapping from the latent Z space to the true image space. So you're taking your latent code Z, and you're mapping it to a point G of Z, which is certain picture in your image space. But this Z is typically something like, let's say, 50-dimensional Euclidean space, okay? And this X space, as I said, okay, for CFAR10, it's 32 by 32 by 3, so which is like 3,000-dimensional space. And that's a deterministic function G. The point is, your model distribution is also supported on low-dimensional manifold in your data space. Right? Because you have 50 degrees of freedom, and as you transform this Z space through G, you will get I don't know how to, right? And this arrow should go on. Okay, you get what I mean. You have certain low-dimensional manifold in your data. Now, the true data is some other manifold in the same space, and it can be something like this. No one actually told you that these two manifolds will even intersect. Okay. If you start training your gun in the beginning, it can give you some crazy other manifold which does not even intersect with the true data manifold. What happens in this case is quite curious. If you take KL divergence, let's say, if you are now computing KL divergence between your true and data distributions, as I said, it goes like P true log P true P model dx, right? And let's say they don't intersect. What does it mean? It means whenever this is non-zero, this is zero. Whenever this is non-zero, this is zero. So I believe you will get infinity. Now, let's look at Jensen-Shannon. You remember what was Jensen-Shannon? So 1/2 KL of P plus Q over 2. Okay, sorry, PX plus PG over 2. 1/2 KL of PG, PX plus PG over 2. So now this guy doesn't go to infinity. But okay, keeping in mind that KL divergence has this form, basically, you will have sum in denominator, right, in both cases. And this sum will basically coincide with numerator, because you will have px over px plus pg. Now, if px is non-zero, pg is 0, and you are getting px over px, which gives you 1, but there is also this constant 2. So basically, it will give you, I think, something like log 2. It doesn't go to infinity, but it takes this maximal value. And actually, Jensen-Shannon cannot take value larger than log 2. So now the point I'm trying to make there is, if you have two manifolds, okay, they are not intersecting. And let's say you are training your model, and you have, let's say, two models, PG prime, PG double prime. They are both supported on manifolds, which does not intersect with a true manifold. But imagine somehow the manifold of this first model is kind of closer to true manifold than the manifold of the second. So what I mean by closer, I mean it's kind of a geometric intuition, but in high dimensional space, this can be a true manifold, and that's your M prime manifold, and this is your M double prime manifold. Okay, they both don't intersect with the true, but this is certainly better than this if you were to choose, right? To choose. If you are asked to choose between these two, I bet you will choose this one. I mean, this is mine, right? The problem is, in both cases, most of the F divergences are giving you the same number. KL divergence will say infinity. So KL divergence between these two is infinity. Between these two is also infinity. Jensen-Shannon between these two is log 2, but between these two is also log 2. So it doesn't discriminate between these two cases. Basically, it maxes out and doesn't give any useful gradient information to train your generator. You could argue like that. Okay, now there can be several remedies. First one would be, before comparing your true data distribution to the model, why not actually adding some noise to both? Okay, so why not doing KL divergence between px plus some noise and pg plus some noise, and let's say the noise is Gaussian. In this case, px plus noise is not anymore supported on a manifold. It is supported on a whole space, because Gaussian has full support. The same is true about PG plus noise. Okay, it's supported on the whole space. Now, because these two distributions have the same support, KL divergence and Jensen-Shannon and other F divergences, they become, better. Meaning this example with supports which are going further away, this example will be nicely covered. Both KL and Jensen-Shannon will give you some sensible information in this case to train your generator. So this could be one approach. Then you will come up with certain problems of, how do you choose the amount of the Gaussian noise? How do you choose the covariance structure and so on? There are papers in this direction. And there is another way to argue, which is, okay, maybe instead of F divergences, we could try to use some other ways of comparing distributions, like IPMs, which I showed you, or optimal transfer. I mean, why not? Why not trying? And first, I briefly mention the path which takes the IPM as a metric of choice. So you remember I showed you this integral probability matrix. I told you you need to choose a function class which defines your probability, your divergence measure. So this slide, I'm sure, will be nicely covered in lectures of Bharat Shriparambudur, who will talk about kernels this week. I'm not going into details. He will show you all the details. But basically, one element of the IPM family is the so-called maximum mean discrepancy, which is tightly related to reproducing kernels. So if you take any reproducing kernel function k, and again, I refer you to lectures of Bharat for that, there is a uniquely defined reproducing kernel Hilbert space corresponding to this function. There's basically a space of functions mapping your input space to real line. Doesn't matter too much. And then you can take a unit ball in this Hilbert space. So Hilbert space comes with an inner product. Inner product gives you a norm. You can define actually a unit ball. Okay, and this BK will be just this unit ball. Now, if you use IPM with this unit ball as your class of choice, you arrive at maximum mean discrepancy, which looks like this. And a very nice thing about it is that this optimization problem actually has a closed form analytical solution. Okay? You don't need to be running this numerically. You know precisely which function maximizes. So this function is called witness function, and you know the optimal witness function. So the idea is now, otherwise, this expression looks quite similar to what GANs are doing, right? As I told you, GANs are taking this optimization problem with respect to this discriminator or witness or whatever you call it, T, and play this adversarial game of minimizing it by making these alternating steps with respect to generator and discriminator. Why don't you do the same here? It looks the same. Why not doing the same? So now, if you do this, you arrive at certain family of algorithms, which you may call MMD GANs, or the other title was moment matching networks. There were several papers in this direction. And basically, the advantage is you don't need to be training discriminate. You know the closed form. So you get, in this respect, you get faster because you're not training discriminator anymore. Unfortunately, there are certain, to actually compute this value, computing this value would be O of n squared. So you will be doing n squared operations where n is the size of mini batch, so kind of it gets more expensive. On the other hand, you could argue that, well, for those of you who knows what RKHS is, another thing is, if the kernel is the so-called characteristic kernel, this is actually a metric. So this is a distance function of the set of your probability measures. It comes with triangle inequality, all the other nice properties, and you lose no. Okay, then it gives you a distance function. So you could also argue that this ball in RKHS, it's kind of a restricted class of functions. Okay, they are not too flexible. They are flexible enough to distinguish between any different pair of distributions, but they are not too flexible, and this may give you a problem. So people tried kind of running this. So I think these papers appeared quite early. Back then, people tried doing it with just one fixed Gaussian kernel, and the results were not brilliant, but still very good results. And compared to a standard GAN, this is more stable. This training is more stable because you don't get this mini-max dynamics of numerical dynamics. Here, you have analytical solution for it. And recently, there was some other approach which says, okay, why fixing one kernel? Why not introducing a family of kernels, okay, and trying to minimize the worst case distance between your model and data. Okay, so you are simultaneously comparing your two models with respect to many MMDs corresponding to many kernels, and you're trying to choose your model such that all of these distances are uniformly small. So this is kind of a stronger requirement than just saying I want to minimize MMD for one piece. So I believe this was done quite recently, and this led to very nice looking results. This approach is actually very reasonable, very interesting. Yet another class of methods, and now I turn to WGANs, they argue in a different way. They also start from arguing, about this problem of F divergences, that you have certain instabilities, gradients vanish, and they max out. So they propose to take one Wasserstein distance. You remember this optimal transport distance, which I was trying to introduce in the previous slide. So this is a particular case of this optimal transport when you choose this cost function to be the metric D defined on your input space. So let's say XD is a metric space, and D defines a metric. If you insert the metric there, you get this one Wasserstein distance, or just Wasserstein distance. And it happens that this is indeed a metric on a certain set of probability distributions. Again, you have triangle, you have all the nice properties. But what is cool about this particular optimal transport is that you have this cool Kantorovich-Rubinstein duality, which says that this optimization problem, which is usually called the primal form, okay, is equivalent to this problem, which is called the dual form. So this equals this. And here, you again have something very similar to IPM. You're measuring difference between expected values of the witness function T, and this function class here is the set of all bounded one Lipschitz functions on XD. So you know what Lipschitz functions are. I don't need to write it down, right? For defining the Lipschitzness, you need to define a metric structure which you have. So here, these functions are Lipschitz with respect to this distance function. Okay? So, okay, now you tell me what do we do next? This looks quite similar to what GANs are optimizing. So let's play an adversarial card, which I already explained to you. And let's introduce this discriminator function T. Let's parameterize it with a deepnet. And let's minimize this thing with respect to G, which will be another deep. So you get, again, this generator-discriminator pair. One trick is you need your T to be an element of one Lipschitz class. How do you do that? And for that, originally, it was proposed that you perform certain weight clipping. So deepness with ReLU, let's say, these are piecewise linear functions. So linear functions, its Lipschitzness is controlled by basically norm of its weights, right? So basically, you can kind of achieve Lipschitzness by clipping weights inside of the deepnet. It was later kind of, they said that that's not the best way actually to perform this optimization. Later, there was another paper which provided a better way to ensure this Lipschitzness, which is basically to perform certain regularization of gradients when you are performing SGD. This is a little detail. But now, so first thing, again, by doing this weight clipping or whatever else you are doing, you are actually taking supremum not over all the Lipschitz functions, but over a certain subset parameterized by deepnet. So again, you will be minimizing, so that, this basically results in the Wasserstein-Gunn approach. So Wasserstein-Gunn, once again, it takes this and it starts playing adversarial training of this quantity, meaning it's trying kind of to minimize the lower bound on one Wasserstein distance. Now, I didn't write it, I was going to, but maybe I skip this. The thing is, if you look at this situation with disjoint manifolds which are going further away, Wasserstein distance is sensitive to this. So it will tell you that as you deviate further and further, Wasserstein distance will become larger and larger. It will be actually kind of linear in this, which was a nice property initially claimed in the original W. Gunn paper. But now, okay, then you get this, at least with clipping, it's very hard to tune the parameter to this threshold at which you clip the weights. However, the second improved approach where you regularize the gradients, it seems to be working much better and more stable and not as hard to tune as this clipping. Another thing is kind of this approach is restricted to a particular instance of one Wasserstein. So I told you, there is this optimal transport family of distances. One Wasserstein distance is only one element. And unfortunately, this Kantorovich-Rubinstein duality, it holds only for this one Wasserstein. You don't get this nice duality for any other C cost function. Even if you square this d, so you put d squared, which will be called 2 Wasserstein distance, you will not get this. So you won't be able to play this adversarial game on any other optimal transport by attacking it from the dual position. Okay, and now that we discussed this adversarial training, and you saw it always kind of goes through the dual formulation. We take what we want to minimize, we find this nice variational dual representation, which expresses things in terms of the soup type of optimization, and we start doing SGD on it. This is kind of a very similar pattern of all the adversarial training. Now I turn to the primal, primal formulation approaches, and we will start with variational autoencoders. I'm sure Max Welling, I know he kind of covered a bit variational autoencoders in 1 or 2 slides, so let me give you a bit of details on it. So now again, let's assume we want to minimize KL divergence between the true distribution and your model. So this we already saw before, right? We were doing precisely that for F-GANs, but there we were doing it through dual. Now what we are saying, so first thing, I already showed you, right? Minimizing KL divergence is the same as, maximizing the marginal log likelihood. This we saw, okay? And maximizing marginal log likelihood is something commonly used, let's say, in Bayesian world. It's something which has many nice interpretations, many nice properties. So this is a very reasonable goal, basically. So let's see what we can do. There is this nice variational bound. Well, I call it variational upper bound. If you flip this minus sign, it will become a variational lower bound. Doesn't matter too much. Basically, it says take any conditional distribution of your latent code Z, given your image X. So remember, we are talking about latent variable models. We have prior over latent codes. We sample a latent code, and then we map it to the true image space, perhaps probabilistic. Okay, these are type of models we are describing. So now take any conditional distribution of latent code given the input image, Q. Then your marginal log likelihood, negative marginal log likelihood, equals this long expression. I could check it right now in 2 lines. Those of you who did it, you know I'm not lying. Those who didn't try it, just try it. It's really one-liner, so it's pure arithmetics. We will start canceling some terms, so I'm not lying. This is not a miracle. This is, it's just equation, expressing things in different terms. But now what is cool? Look at this term. What can you say about it? It's a KL divergence. Oh, one thing I didn't mention is KL divergence is always non-negative, okay? And it becomes 0 only if 2 distributions coincide. So now you're subtracting something non-negative, right? So you can forget about this term and get an upper, okay? I just erased this term, and I have this, okay? So now, moreover, look. The left-hand side does not depend on this Q conditional, right? It's independent of Q, which in particular means that if Q is not restricted at all, if you are allowed to use any Q you want, minimizing this upper bound with respect to Q will precisely give you the negative log, marginal log likelihood. So, this you can just check by inserting instead of Q of Z given X, precisely PG of Z given X. This term cancels. And you just recover, this upper bound. Okay, so if you take inf of this upper bound over this Q conditional, you recover marginal log likelihood. So what I want to say is that you can use this as an upper bound on your negative marginal log likelihood, but there will be a gap. Okay, and this gap depends on the flexibility of your conditional Q. So in the world of VAEs, this Q is called encoder. And the G, this PG, is called decoder. So now what you can do is, I didn't write this down, but perhaps I should have. So you can replace inf with respect to all Q functions, Q encoders, by inf with respect to, let's say, encoder functions parameterized by deep nets, right? This gives you some, some restricted class of encoders, and this will mean that you're not getting equation here, but an upper bound. Okay? And the gap depends, as I said, on the flexibility of your encoder family. So now how does variational autoencoders proceed? They choose certain, let's say PZ. Does PZ appear somewhere? Yeah, PZ. They choose your prior PZ, let's say again, standard Gaussian. Let's choose your decoder distribution, the way you map Z to X, anything you want, like, let's say Gaussian, okay? So Gaussian with expected value G of Z, where G will be some deep net, and with certain, let's say diagonal isotropic covariance structure. So take Gaussian PZ, and so this is something original variational autoencoders did, is they said, let's use Gaussian encoders. So encoder, as I said, is a conditional distribution. It takes an input image and it returns distribution over the latent space. Original VAs were using Gaussian encoders. And why is that? This is because you want to have a tractable form of this KL term. If your PZ is Gaussian, you can compute KL divergence between two Gaussian. And it's very hard to develop an analytical closed form for KL divergence between Gaussian and something else. So if you choose Gaussian PZ, it was reasonable to use Gaussian encoders. But keep in mind, okay, this reduces, this potentially increases the gap between your upper bound and the true quantity, because as I said, you restrict yourself to certain family of encoders. And the more flexible this family is, the smaller is the gap between the bound you're optimizing and the true thing you want to optimize. And here, you're making quite a hard assumption that your encoders are Gaussian. Gaussians are not too flexible, you could argue. So, but still, this, they had to do that because of this reason which I said. And finally, what they said, let's parameterize this expected value of decoder, expected value of encoder, and even covariance structure of encoder using deep nets. Stick it back here and run SGD. So basically, you will be doing now inf over G of this quantity, where this inf would be over, Q of this form, meaning over another mu deep net. So now you have basically the mean type of optimization problem, where you have certain deep net layers, so means, in this covariance structure, and you can be just backpropping through these networks to perform SGD of the marginal log likelihood. So you will be you will be maximizing the lower bound on marginal log likelihood. In other words, you will be minimizing the upper bound on KL divergence between your model and your true distribution, which we already discussed is quite a reasonable thing. Okay, compared to GANs, all the GANs were minimizing the lower bound, which is, okay, a bit weird thing to do, minimize the lower bound. If you want to minimize something, you should, at least you should be minimizing upper bound. But GANs are doing minimizing the lower bound. Here, we are minimizing an upper bound, actually. So I will mention this perhaps a bit later, but basically, this makes this whole process very stable. Mean in this respect is much better than min-max. You don't get this bad dynamics, and you don't need to schedule between this, iterating steps with respect to discriminator and generator. Here, you're just doing min. You're just performing gradient steps with respect to all parameters of all these deep nets. Now, regarding this gap, as I said, this restriction to Gaussian encoders, it may be restrictive. It may make your bound, which you're optimizing, not so tight. So you may end up minimizing certain upper bound, which is not well aligned with the quantity you actually want to. So how would you reduce this gap? So one possible approach is, allow for more flexible encoders, right? This is reason. And there was this approach called adversarial variational base, which does precisely that. So Once again, this is what VAE is doing. So VAE is optimizing, minimizing this upper bound with respect to this G function, okay? And for VAE, this Q calligraphic is a set of Gaussian inputs. So now, let's make Q calligraphic larger. Let's actually say that Q calligraphic will be all the probability, all the conditionals implicitly encoded by the random variables of the form, some function of X and noise epsilon, where epsilon is your noise of your choice. It can be, again, Gaussian, whatever noise you want. But basically, this is a random variable, right? Because this epsilon has a stochasticity. It is random. So you're taking X, you're taking some random variable, and you're mapping them through certain transformation. This quantity is random, and this quantity follows certain probability distribution, which we will call QE of Z given X. And we will say that it implicitly defines this encoder distribution. Now, if we choose E to be any flexible function of our choice, and of course our favorite choice is huge deep net, it gives you quite a flexible and rich class of encoders. That's great. Maybe we reduced this gap between the variational upper bound and the marginal variational lower bound and marginal log likelihood. But what's now the problem? The problem is how do we now compute this KL term? If PZ is Gaussian and Q is of this form, you cannot perform it closed form. So the idea was, now that we have all this, rich literature on adversarial training, you can use adversarial card to estimate this term, right? I told you that GANs and F-GANs and W-GANs, they are all approximating F divergences or Wasserstein distances with optimization, with adversarial training. So what was proposed is now to take these encoders and to replace this scale term with its adversarial approximation. So you will introduce a discriminator. Otherwise, objective will stay the same, but now there will be extra player in your game, which will be this discriminator, which you will need to tune from time to time to perform adversarial approximation of this term. So you will kind of get back to the min-max type of problems. And now what you get is not anymore an upper bound on the negative marginal log likelihood, but, well, you actually don't know what is, right? Because you had an upper bound, but then you switched this with a lower bound, this term. So overall, it's still equation. But you know that if discriminator is powerful enough, you will, in limit, it's called non-parametric limit. So if your deep nets are flexible and deep enough, let's say, and if you can recover any function with your deep nets, then you will be getting precise estimate of KL divergence, and then you fall back into minimizing upper bound on negative marginal log likelihood. So this was kind of this approach. So you see that all these methods, they are attacking KL divergence minimization from its primal formulation. Now, there are certain downsides of these methods. First, so they were introduced originally before GANs, and they look so great. You just minimize it, it's stable, it works fine, it has all these nice log likelihood interpretations. It comes with encoder even, right? Because GANs don't have encoders. An encoder, this Q distribution, it can often be used as a feature representation for your input image. What you can do is once you train this model, you take your encoder, you take an images of your training sample, and you map them to the latent space. And this gives you a low-dimensional feature representation of your training set, which is known to be very useful in various supervised, semi-supervised type of problems. GANs don't have that. They don't have encoder. Here you have encoder. The problem was that, at least with images, literature reports that these VAEs are producing a rather blurry looking image. So I will show you many pictures a bit later, but this was the main kind of problem, the blurriness. And to kind of try to explain you why this happens, and also to explain another effect, another problem of VAEs is when you train G, so only this term depends on G, right? G is your generator, so decoder. So now this Z is an input of your decoder. Decoder is a function which is like generator. It takes a latent code and it gives you an image. In GANs, it was deterministic. In VAEs, it's usually probabilistic. But now you have the Z space, right? In which part of this Z space are you actually training decoder during VAE. You're actually training it on a very specific part of Z space. So this is X space. You see, Z comes from Q of Z given X. And then again, X comes from PX. So when you train your decoder, you are training it only at the points which are encoded through training images. So in your input space, you have a bunch of training points. You remember, this was a manifold of true data. So these are your training points. Q maps those to the latent space. So these are Q of Z given X. And G is trained only on these images. Now, when we sample from our model, what do we feed to G? Our model is a latent variable model. We sample Z from the PZ distribution and we feed it to the generator. Now, there may be a mismatch between these points where you trained your generator or decoder and the points where you will actually be applying. So, in other words, it may be the case that your decoder is doing perfect job in reconstructing training images, but it never saw points which you will be receiving when you will be actually sampling the model. And you don't have a control of what the decoder will be doing actually in these parts of the space. And also, because of this KL term, this thing is, because of this KL term, encoder is enforced to map through data points. So now let me put Z space as a Euclidean space, because most often Z is a Euclidean space. It forces the true data points to be kind of mapped to the center, because PZ is usually a Gaussian, standard Gaussian center, right? And you're saying, okay, I want Q to be rather similar to PZ for all the X's. And this leads to the images of different training points to largely overlap. Okay? And this is linked in the literature to this blurriness effect. So, the formulation of VAE itself kind of forces these balls to intersect, which leads to blurriness. Sorry. So far, so good. I hope. Not sleeping. I'm trying to be loud so that you cannot sleep even if you want. Okay, so there is another also part of this primal story, which is, actually, let me do this, the whiteboard. So usually, this term is called reconstruction term, and the first term is called, KL term or the regularization term. And let me tell you why is that actually. So let's assume our decoder is Gaussian. Okay, so let's assume that the PG of X given Z is a Gaussian distribution, as I said before. So X with parameters G of Z, and let's say some sigma squared times identity. This is our model of choice. Okay? So let's write down what is this actually, this term. Log PG of X given Z. Well, it comes with minus. You know that PG is of the form e to the minus distance squared over sigma squared. Now you take log, exponential disappears, minus cancels with minus, and the second term will have a form x minus g of z squared over sigma squared. Well, 2 sigma. Right? Read. Now you have this KL term. Now you see this sigma enters only in the second term. It does not appear in the first term. Okay? So if you choose this sigma squared to be fixed, you're not training it, let's say, during the VAE run. This sigma squared, you can view it as a regularization coefficient. Basically, it weights these two terms. Now, funny thing about VAEs, you cannot set sigma squared to 0. Because in this case, your log likelihood, this term, first, okay, it will become infinity, but most importantly, this will correspond to Dirac delta measure PG, and you cannot differentiate it with respect to the G parameters. Okay, it's not differentiable. You cannot train it. This is something weird, because when you train VAE models, in the end, when sampling from it, you will just return G of Z with Z sampled from PZ, right? You will not add a Gaussian noise on top of G of Z. This Gaussian noise, you know, this Gaussian noise, you use it to tune the model. But when you sample from the model, you will not add the Gaussian noise. So this basically corresponds to a mismatch between the model you train, because you're training this model, and the model you use while sampling. So sigma squared equals 0, something impossible for VAE. But now, basically, still you could kind of argue that, okay, sigma squared equals 0 means you stop caring about this term, you only concentrate on this. This basically corresponds to the unregularized autoencoder models, which were historically before variational autoencoder. So all they are trying to do is to minimize this term, which is they are trying to minimize the reconstruction cost. Encoder and decoder are trying to arrange in such a way that after encoding into the bottleneck space Z, decoder is still able to reconstruct the samples of training images. This works very nice, but there are certain downsides, which are, so, okay, what I say, yeah, so if you run this, you will notice often, it can happen, that the true images ends up being mapped into certain spots of the latent Z-space chaotically scattered all across the Z-space. And it's very hard to sample those models. Plus, these Z encodings, they don't give you a very nice representation of your data. So this is something which is known for unregularized autoencoders. This is why people start, okay, maybe this was not the reason, but variational autoencoders in this respect are better, because this part is not true for variational autoencoders. They really care about structure of the encoded Z-space. This is what. Okay. So finally, I hope I have some time. Yeah, I still have time. So now we already talked about minimizing one Wasserstein distance through its dual formulation. It was of W-GAN. Now, let's try to attack. Oh, I had some messages. I was afraid this will happen. I think I even turned off the Wi-Fi. Why am I getting messages there? Now I'm not. What was it? Okay, so now let's be more ambitious. And let's say we want to minimize actually optimal transport for any given cost function C. So you remember, W-GANs, I told you, this nice Kantorovich-Rubinstein duality holds only for particular element of optimal transport family. Now let's try to attack all of this. So it happens that if you try to use this as a measure of similarity between your true and model distributions, this is this optimal transport I told you about, and this is a space of couplings between two distributions. So now, if your decoder function, PG of y given z, which is the generator, if you will, is deterministic, like in GANs, you can show that this problem is actually equivalent to this problem. So here, what you have, just to compare, is very similar to the minus log likelihood. Okay, this term, you have px, qz given x, the same you had here, px, qz given x. Here you had log likelihood, here you have the cost itself. Okay, so this looks quite similar to the reconstruction cost part of the VAE. But now, these encoder functions q are constrained. So I will speak about this constraint a couple of minutes later. Let's now have this kind of intuitive picture representation. So these are circular points, the true images from our true data set. Okay, so this is support of the true data distribution. Square picture, square objects, these Y objects are outputs of our model distribution. We are trying to find kind of this coupling between these two. But we know that we are using a very particular model, right? Latent variable model. And we know that every one of these, they were produced by certain latent codes, right? And we are using the deterministic mapping. So we are mapping certain latent codes in the Z latent space to these points. So instead of trying to search this coupling in X space, why not going through the latent Z space? So we can try to couple the input points X with a latent code Z, and then Z codes are already coupled with the fake images, with the model images, the square points, right? So this is a kind of an overall idea, and this idea introduces encoders into the optimal transportation world. Because here you don't have any encoder function. You are only arguing in terms of coupling between, pictures. Here you get those encoders, but they are now constrained. And what is this constraint? Boom. All the time. This QZ distribution, what is this? So the constraint says, if you have your Z space, no, let's go. So that's a Z space, that's your data distribution. And you have kind of this, PZ prior over your Z space. So this constraint, what is this QZ? You sample from your true data distribution PX. Let's say these are your training points. So you take any one of them and you map it. You map it using this encoder to the Z space. Okay, encoder is a probabilistic mapping. So you get certain distribution here. Then you map this one, you get certain distribution here. So if you marginalize out PX, what you will get here will be called QZ. It's also called the aggregated posterior, so you can view it as Q of Z given X, PX of X dx. So you are marginalizing out the true data distribution. This distribution is called QZ, is denoted QZ. And here I'm saying that I want this QZ to actually match my PZ. So remember what I told you about variational autoencoders? The decoder there is trained only on the encoded true images. But we sample from PZ and there can be this. If this condition, so QZ is precisely the distribution of encoded true images. If this happens, we will be sampling exactly in the parts of the space where we trained our decoder. So this is already nicer compared to VAE. But okay, this is a certain constraint. Basically, another interpretation is instead of KL term appearing in VAE, so in VAE you have this KL term, right? PZ, right? And you have expected value with respect to the data distribution. This is what you have in VAE. This means taking this expected value inside. So expected value of this with respect to true data distribution is exactly QZ. So in VAE, you're saying every point should be mapped kind of, centrally, which leads to intersection of these balls. This says you can have something like this. You can map this point here, this point here, and this point here. And when you take a mixture of all these blocks, you want to get something like this. So you can get this match QZ and PZ without making Q of Z given X to intersect for different X. So now, but we still have a constrained variational optimization problem. So variational optimization problem is hard. Constrained one is even harder. And this constraint is a rather nasty. So what can be done is, you can always relax your constrained optimization problem doing penalization. And you can introduce certain penalty. Okay, so now you can take inf over all the encoder functions you want. This term stays the same. And you add certain penalty. And let's say this d of qz and pz is such that when pz coincides with qz, you get 0. Okay. In this case, from the convex optimization world, you can find certain results saying that if you start enlarging this lambda regularizer coefficient to infinity, then basically if this d is convex and some other regularity conditions are met, this becomes equivalent to this. Of course, in practice, we are not going to do that. We are just going to choose certain regularizer lambda, which we now treat as a hyperparameter of our model. And this d, you can choose any, I don't know, f divergence between qz and pz. Let's take, I don't know, Jensen-Shannon divergence. So then this penalized optimal transport or POT algorithm, it does precisely that. It replaces this term with any f divergence or, I don't know, Wasserstein distance if you want, and plays an adversarial card on this term, to estimate this term adversarial, as I said before. And then you can just start playing the SGD game with all the deep nets and do precisely the same as we were doing before. So now this is different from VAE in many, many different respects, as I said. And this is approximately minimizing the optimal transport through its primal, okay? Because we are doing things primals, not dual. Okay, we get this this minimax dynamics by approximating this with adversarial training. But you could imagine, this can be literally any convex divergence function. So you're not, restricted to be using f divergences, or you don't need to play the gun game. Moreover, this happens in the Z space. Here you're comparing distributions in a Z space, which is smaller than the picture space. And moreover, one of these two distributions, PZ, and you can sample from it and it analytically, let's say Gaussian. So if you develop any way to check that QZ is Gaussian, through which you can backprop, that would do. Like you can use certain moment matching, whatever you want. So now just to wrap up with this part, if you choose C equals squared distance, here, it will be the same as kind of doing this VAE, which I showed, right? You get this squared distance over sigma squared, but you also now have this constraint, that is PZ needs to match QZ. This happens to recover already published algorithm called adversarial autoencoders. This AAE was introduced kind of heuristically. They didn't actually say that it corresponds to minimizing the optimal transport, and now we know that it corresponds to minimizing 2 Wasserstein distance. If you take oh sorry, I wanted to drop the upper, so this 2 should be a subscript. If you just use the Euclidean distance, you will see that this is the same as minimizing 1 Wasserstein distance through the primal. Wasserstein gun is doing the same through the dual. So this is an interesting duality. And as I said, you get this nice thing that these balls don't need to intersect anymore, and this intersection of the Q balls, this is linked kind of to the blurring. So the hope is this is not blurry. And I have 8 minutes remaining. I turn to the final part where I finally show you some pictures. No pictures before that. Now I need to show you some pictures, otherwise you will hate me. Lots of boring math, huh? Okay. So let's start summarizing GANs and generally adversarial training. So adversarial training is about attacking things from the dual perspective. GAN, F-GAN, Wasserstein GAN. It's all about going through the dual. They are known for producing very sharply looking images. And there is a kind of so sharply looking would mean something like precision, There is this precision recall type of compromise, so this is precision. And this could be explained by the fact that if you look at what the generator in GANs is trying to do, G is trying to maximize this type of stuff. okay, where T is certain trained discriminator function. So you see that the cost of generating unrealistically looking image is very high. So in GAN generator will make sure that no matter what it produces very nicely, sharply looking image. This may actually lead to one of their problems, which is the mode collapse or mode dropping. So GANs may start concentrating on certain part of your data distribution and dropping all the other modes. And they are unfortunately known, so they are very hard to train and they are rather unstable, although many people here, I think, would disagree if you tried. Okay, so some people think that GANs are perfectly fine to train, but this knowledge you get in many months of running them, then you know all the tricks. You have this huge list of tricks like, you know, the label smoothing, adding noise there, and this and that, and balancing the discriminator generator steps. Once you all know all these hacks, okay, apparently you can train them and they give nice results. But overall, they are unstable and hard to train. And they come without an encoder. So basically, all you can do with GANs is to sample from them. So you could argue, okay, but you also have the trained discriminator. So maybe if you take certain feature representation appearing as a layer in discriminator network, maybe this feature representation will be good for representation learning. Keep in mind that discriminator is chasing the current generator. You're training them together. So generator may be concentrating on artifacts of your current model, meaning discriminator will be trying to capture those artifacts. And it may happen that you show a blank image to discriminator and it will say, oh, it looks exactly like a data, just because those artifacts are not present in the blank image. So now here are kind of pictures from many of the GAN models which I found. Okay, so those which we all tried and which are known. So you see, so this is on a small ImageNet, 32 by 32. This architecture called DC GAN. So you see sharp images, right? They kind of look sharp. There are those sharp edges. So the thing is, okay, it's hard to tell what is on this image. They kind of look sharp, but if you are asked to tell what is there, you can have a problem. Now, they can be trained even on huge, high-resolution images. So these are 128 by 128 ImageNets in this paper improved GAN. So you see, these are kind of docs. You have a texture, you have a hair, and it all looks sharp, right? So it's cool. But there are kind of, these global statistics are kind of, you know, global structure is not correct. Like, you don't have legs and so this is yet another model, the improved WGAN, which I mentioned. So again, sharp. You kind of, okay, this is kind of, that's a track, right? So this is CFAR 10, okay? But this car, so this is type of artifacts you often get with GANs, you know, somehow this color transition and, you know, this car looks like a car after the crash, after crashing to the wall. And I'm not trying to say that GANs are bad. I'm just trying to show you what type of effects you get. They are certainly very sharp, which is very hard actually to achieve, and this is good. This is yet another. This is MMD GAN, which I mentioned, and this is another paper from Sebastian Novozin. This stabilized GANs and still sharp, and you still get some tires. So maybe this is a plane. So you can kind of say what is on them, like horse or I don't know. This is again the car. Another thing which I didn't mention, actually I mentioned, right, that this latent space representation is actually a nice feature representation. It actually has some manifold structure. Unfortunately, with GAN, you cannot reverse it. You cannot take an image and get the features. But what you can do is you can take a bunch of points in the Z space, start interpolating between them, so moving on lines connecting those points in Z space. And here I'm showing what you get if you apply the generator function on these points. And this is on this LSUN bedrooms dataset, 44 by 44 DC GAN. So basically, these are this is what the trained generator is producing. And you see a nice smooth interpolation between various different bedrooms. So, okay, what they usually mention is sometimes you see the window you know, being shifted, then disappearing and turning into TV and then something. So you have this nice geometric linear manifold structure in the Z space. Now then you can play these games, you know, this arithmetic. So if you take average, so you take these pictures, they are Z representations. You average over them, so these are smiling women. You subtract the average Z for the neutral women, and you add average Z for neutral men, and in the true image space you get a smiling man. So this shows that there is certain manifold structure in that, which is very useful. And now I told you don't get encoder with GAN, but you can try to invert the decoder, meaning generator, meaning I give you the true CFAR image, and I'm asking you to find such Z that G of Z looks similar to this image. So this is kind of a point inversion of generator. And then you see that trained models are actually capable of producing CFAR images. The only thing is you need we don't know where Z points corresponding to these images, we don't know where are they in the Z space. And they can have very small mass under PZ. So maybe you will never sample those. At least we see that generator is capable of producing. With VAEs, you are doing things in primal. This leads to very stable training, very kind of high recall, meaning diverse samples. You don't get this mode collapse issue. And this can be explained by the fact that generator is trained to perform something like this, where you see that you need to be able to reconstruct all the training points, meaning you cannot drop any modes. And they come with encoders, but pictures look blurry, okay? And now there are many papers saying we want both precision and recall, and we want stability. So why don't we try to merge these two approaches? And there are various papers trying to, you know, perform this, instead of cost function, to use some adversarially trained function, or combine auto-encoding type of costs with GAN criteria. There are many papers appearing. I think this is a very reasonable and promising direction. And just to show you some of the VAE samples, so this is from adversarial variational bias. Indeed, you see blurriness, right? Kind of, no matter what blurriness means, you kind of see that they are blurry. These are our trials with vanilla VAE on CFAR 10 with certain architecture. We are using a very little bottleneck, so 20-dimensional Z space. So kind of, again, I mean, this is enlarged low resolution, so it gets a bit pixelized, but you see kind of the blurry. There is nothing sharp in them. Then if you do this spot with the same architecture and the same 20-dimensional space, you start getting something like this. So, okay, maybe a bit sharp, a bit more sharp. So, kind of. This is just to show you what. So these are primal type of approaches. Okay, so you kind of have diversity again, right? So all these examples, they were not collapsing at any given modes because I was showing you these examples. But often, if you run them, they will collapse to producing only similar images. Here, we never observed these models collapsing, never, and they were always stable. And this is a final slide to say we arrived at. I showed you many models. I showed you many pictures. Visually comparing them is not good enough anymore. This is the claim. We need to come up with certain evaluation metrics. People use nowadays something called, let's say, inception score, which is basically feeding samples of your model to a trained CFAR 10 classifier and making sure that the classifier will make a certain prediction saying that this picture belongs to a certain class. This would make you believe that sample looks reasonable for CFAR pre-trained model, right? But then there are all these questions like, you can then just start showing the same CFAR example to inception score, and you will get a very high score, and yet the distribution is wrong. And for problems like this, you can start measuring reconstruction in this respect. So measuring, is your generator capable of producing realistically looking images? But this doesn't mean that you are actually able to sample those from your model. So this is again a problem. This is a very fundamental problem of the field, and we expect that next big step is actually to come up with a way to evaluate. And I hope you all now kind of have this big picture of what is happening in this field. I hope you're interested, and I ask you to concentrate, to focus on this question. You are all very smart people, so let's crack this. And yeah, so that's it. Thanks for being this. Yes. Thanks for following the talk to the end and not falling asleep. 1 hour 35 minutes, so 5 minutes over time. Yes. Do we need a microphone?
It seems to me that so you have a data that is generated mechanical that then you do all these things. You are going outside that class.
Which class?
The class that your data is generated. Like in this marginalization, essentially you're going to somewhere else, and at some point you want to be close to that, either by matching moments or something like that.
Are you talking about this QZ PZ issue or
no? The previous at the beginning you started with this VI variational method.
Variational auto input.
Yeah.
Yes.
So my question is that if you know here, okay, if you know all these things, is it possible to do kind of plug-in methods? Just stick with the class that you know your data is generated. So how does it compare if you don't go this route and then compare?
If you know the class, so you're saying, let's say we know the true data generating model?
Yes.
And we want to perform this knowing the class.
Yeah, exactly.
So it should converge to this true model.
And then how different will be if
okay, I mean, okay, up to this gap.
Yes.
So what you always need to remember is that you're not actually minimizing negative marginal log likelihood. You're minimizing an upper bound. And the question is, how large is your gap? Which is, I told you a way to kind of improve it with this adversarial variational bias, but still the gap is there. And here on top of that, you get all this nasty minimax dynamics from estimating KL. So even if the model is well specified, even if you know that it is contained in your class, you may end up with something different because of this gap. So certainly your true model will minimize this upper bound, but there may be many other models minimizing. Actually, this is even not true. So the fact is, you know, the true quantity you want to minimize may look like this. Okay, so this is kind of the models. And the upper bound may look like this, which has nothing to do with the true quantity. So your true model may be actually maximizing your upper. So that's quite, yeah, this is what you get when you start minimizing upper bound. But we run these methods and we see that they're doing a reasonable job. Kind of our empirical knowledge shows that maybe this gap is not too huge. So at least we are getting some reasonable signal there.
Is there any case that you can reach that bound, essentially, for example?
EM is still variational lower bound, right?
Make sure that
yeah. Okay. Yeah.
The whole point.
If you know that your true model is precisely this many Gaussians which you are using, and you know, then okay, yeah, achieve it. Sure. But again, that's a very, very, very strong constraint, right? You know that your model is mixture of Gaussians, like K Gaussians, and you are the true data is mixture of K Gaussians, and you're doing a model which is also a mixture of K Gaussians. Yes, but we have no idea how the true data distribution looks like for CFAR10 given MNI. It's quite like this parallel is tricky. I'm not sure if you can actually achieve the zero gap. I hope I answered your question. We can discuss offline. Yes. Attack me offline. I'm here all the week. Hey. Thanks.